Continue. We're going to try to understand a structural derivation of this Verlinde formula. Now, I've spent the last hour and a half reading this book on its derivation of the Verlinde formula, something I've never previously gone through before, and I understand it 80%. Hopefully during this lecture we will make it 100%, but let's see. Okay. Okay, excellent. So just let me remind you what we're trying. You remember that we had this, if you had OI with OJ, the fusion of this can produce the operator OK, but it needn't produce it one time. Okay, you could produce it some integer number of times, and that integer we called Nijk. Okay, so these integers are the Verlinde fusion coefficients, these Nijk. You remember in the last lecture we discussed how there was an analog of these things in group theory. The number of times you fuse representation 1 and representation 2 produce how many copies of representation 3 you produce. And you remember we discussed how simple properties of this thing tell you that if you regard Nijk as a matrix, as in the ith matrix with jkth elements, then these matrices commute with each other. Okay.
So is this thing closes itself? I mean,
what do you mean closes?
Closes means Y and OJ.
Mm-hmm.
Opposition is something OK which belongs to the set or something.
Yes. So when you fuse OI with OJ, by the state operator map, whatever you get can be expanded. So so the question is there a basis for these things? And the answer is yes. How do we know that? We know that from the state operator map. You see, when you have OI with OJ here, okay, we do the path integral with these two insertions. That's something. That's some state. And that state then, by shrinking the sphere in the usual way, is some operator. Okay? So OI with OJ is some local operator. And since Ij are primaries, they plus their descendants are all the local operators. Okay? So then a one-to-one correspondence with the set of states on the sphere and completeness of the Hilbert space, the fact that any state in the Hilbert space can be represented as a linear combination of basis elements states in the Hilbert space, tells you that this always closes in the sense. Okay? So this is in the case of a conformal field theory is a proof. Okay, excellent. So great. Now, fine. The question we're trying to address, okay, is does this Nijk have anything to do with these other elements that we talked about, namely these modular invariant Sijs? You remember what the Sijs were, right? It was, if you take this character, you remember the character Kij, which was trace in the jth representation viewed this way. Okay? And then you tried to represent that in terms of traces viewed that way. Okay? Yeah, so Kj could be written as Sji, or maybe I can't remember all the conventions, but let's say Sij, Kij. Okay? This was what you call the modular transformation matrix. Okay? So the characters viewed this way, expressed in terms of characters viewed that way. Okay? Or equivalently, modular transforms, or modular transformation of the character was written in terms of other characters. The tau goes to minus 1 by tau of the characters was written in terms of the other characters. Okay. So these look like completely distinct things at the beginning, but they're not. In fact, you remember we discussed last class that these n matrices were simultaneously diagonalizable because they commuted with each other, and that the unitary transform that diagonalizes them, the unitary transforms that diagonalizes them, is in fact this S matrix, which we previously argued was a unitary matrix. Okay, So now I want to try to give you a sort of abstract proof of this statement. Okay, and it's okay. So let's start. What we're going to do is define a few linear operators. Okay, so let's start with the following. Suppose I take the following conformal block: I star 0, j, j star. Okay, so what does this mean? This has operator I with I star fusing to give you the identity representation, and then unfusing to j with j star. J with j star also fusing to give you the identity representation, those two fusing with each other. Okay, now when we talk about conformal blocks in general, precisely because the number of ways of fusing two operators to give a third is not unique. In general, if I wrote down a conformal block like this, I, j, k, l, m, the notation would be incomplete. I would have to tell you which fusion product I choose here and which fusion product I choose here. Because there are n ij k distinct ways of coupling ij to k. And unless I tell you which one I'm choosing, that's not complete notation. Okay, and that is what we will need in general. However, in this very specific case of I with I star fusing to identity, there's exactly one way for I with I star to fuse with identity. This is the same statement as the 2-point function of I with I star is unique, because that's the fusion to identity. Okay, so for representing this conformal block, I don't need to give you any additional data. I don't need to give you the alpha and beta couplings. Okay, because just like I with I star, j with j star fuses to identity in a unique way. So this is a well-defined conformal block without giving additional labels. Is this clear? Okay. Now, crossing tells us that any conformal block can be re-expressed in terms of conformal blocks like this: ij, k, I star, j star. But now I have to specify what coupling and what coupling. Okay? So, this quantity, so this any conformal block like this, okay, any conformal block like this can be written as sum over some numbers. We don't know what they are. Okay, I'm going to call them A, alpha, beta, and then the notation should also have I, j, and k in it. Okay, so if we wanted good notation, we should also put I, j, k. But we're going to omit that in this discussion very soon, because the notation will get too cumbersome otherwise. So we're working with some fixed I, fixed j, and fixed k. We're keeping track of these alpha beta labels, but always keeping in mind I, j, k. So 3 fixed operators. Okay, but for any given I, j, k, so we can rewrite this block in this way. That is the statement of crossing. Is this clear?
So this side is not the sum of 2-point functions.
This side is not the sum of 2-point functions because it's not fusing. It's I with j fusing to k. It's not I with I star. Right? So it's non-trivial 3-point function. The 3-point functions that are trivial are ones that involve identity, because then they become 2-point functions. Okay? But here we've got each side of the fusion involves a non-trivial 3-point function, so it could occur many times. Clear? Okay. So let's keep this notation for a little while. I'll call this ijk. Okay. By the way, in group theory, there is a similar kind of object. It's called 6J symbols. I'll just remind you of that, so just so you have a mental analogy in your mind. When we study SU2 group theory, we ask the question, How can you make singlets out of fusing J1, J2, J3, J4? J1, J2, J3, J4. And the point here is that there isn't a canonical way to do it. Any good way of finding a basis of this set of singlets involves choices. One choice is to fuse these guys. Fuse these guys. Fuse these guys to some Jm. Fuse these guys to some Jm. And then fuse the Jms. Okay? So that would be the analog of this. Let me draw that this way. J1, J2, Jm, J3, J4. Okay? But another way would be to do the analog of this. J1, J2, J3, Jn, J2, J4. That would be a second way to do it. You understand what I mean, right? You do Clebsch-Gordan decomposition of these two, you get some spin-end particle. Clebsch-Gordan of these two, you get spin-end particle, fuse the spin ends. That gives you an invariant of SU2. Now, this is one natural basis for invariance. This is another natural basis for invariance. Any invariant can be written as a linear combination of these or as a linear combination of these. Therefore, this in particular can be written as a linear combination of these. Okay? Now, these guys have J1, J2, J3, J4 in common. But, so that's 4 J's, but a 5th J here and a 6th J here. So these coefficient matrices that express one in terms of the other depend on 6 angular momenta and therefore called 6J symbols. Okay? So these are the conformal analogues of 6J symbols, except for the fact, conformal field theory analog of 6J symbols, except for one fact. We are looking not at the most general, the most general would have been I, J, K, L. We're looking at 6J symbols with the 4 external particles chosen to be rather special. Okay? I star, J, J's. Okay? Because that's what's going to be useful for us. So these A's are particular examples of the conformal analogues of 6J symbols. Conformal field theory analogues of 6J symbols. Is this clear?
So J1, J4 fusing also possible?
Yeah, J1, J4 fusing also is also possible. And that would give you, basically, it would be another example of a 6J symbol. You see, you choose J1, J3, J2, J4, and J1, J2, J3, J4. But you could choose, as you say, J1, J4 fusing. It just changes the identity of what you put inside your J's. Because they're all on the same footing.
So the 6 will remain.
It's not that. It's just yet another basis. Just with the J labels interchange. Okay, excellent. Excellent. So these guys are going to play a role in what we're going to talk about. So these are these A's which depend on I, J, K, alpha and beta. This is clear. So this is our first definition. Our second definition is the following. Okay. Consider the following. I star, K star. I star, K and K star. Okay. And let this guy be a J with an alpha and a beta. This defines some conformal block. Again, the kind of conformal block that has the external particles equal and opposite in pairs. I star, K star. Okay. Now we're sort of going to try to undo the previous operation. So this guy can be written in the following: I star M K star. right? As some linear combination of these. That's what crossing tells us. Once again, we don't need to put which fusion labels here because one of them, oh, sorry, in general, we need to put which fusion labels here, zeta and zeta prime. So in general, we would write B, which is a function of zeta, zeta prime, and then a function of, let's call it zeta, zeta prime, and then a function also of alpha, beta, so a lot of symbols, alpha, beta, zeta, zeta prime, and then it's a function of which external particles, so I, k, and what runs in the middle, m. Okay, and then you would write this as a sum over everything. Just writing down crossing. Okay, now in what we will be interested in this lecture, we will only be interested in the part of the right hand side that has m equals 0. Okay, so for the part that has m equals 0, okay, for that part we can ignore the m label because m is 0, and also zeta and zeta prime are irrelevant because you're fusing to one of the fusions is identity. So while if you want to write this as something, we're only interested in a part of the right hand side. Okay, the part that projects onto 0 running in the middle. It's sort of the inverse of this operation, where we have 0 running in the middle and you did this. Well, we're sort of inverting that. Okay, so since we're interested in that, we remove these indices. So it depends only on the external labels I, k, and alpha, beta. Okay, now you have to remember that this is no longer an equality. This is equal to this, some projector. The part that has 0 running in the middle is equal to that. Is this clear? Okay, just what these guys mean. Excellent. So we've defined this is the definition of these B coefficients. Finally, I'm going to define one more number. Okay, and this number depends on I. Okay, so but let's see. Suppose I have I star, and we have this conformal block. I star, I. Once again, we don't need to specify what fusion because there's 0 in the middle. In general, we can write this in the following form. I star, then anything running here, we'll have to specify the fusion and so on. But we're only going to be interested in what happens when this guy runs. So we once again look at the projector of this. 2 I star I. Okay? Now, this guy is just a number. The coefficient behind this is just one number. There's nothing it depends on except I. Okay, so this defines this coefficient, this symbol mu I. Are these three definitions clear?
So is it like A comes with these identities which are some operators?
Yes.
And then if you multiply A's and B's, then you should get a projector.
If I multiply A's and B's, yeah. So had B been everything, A with B would have been identity. Okay, because A and B would have been inverses of each other. Yeah, but if I multiply A and B, it's true. So I do this, and then I use on this. You see, A times part of what you get with B will give you back your thing. So now what does that mean?
On the left hand side, you just have identity block.
On the left hand side you have what you have. I star 0.
It has a linear combination of
All kinds of things.
Many things.
Yes.
But now you're again extracting from those things just the identity block, right?
Yeah, you're extracting just from those the identity block. That sounds right. Give me 1 minute. Okay. Yeah, it feels right. Feels right. That if you do this, and then you keep only the identity parts, you should just get back to yourself. Yeah, I think that's right. I think that's right. I think that's right. Once you do the sum over k. All right. Yeah, and sum over alpha and beta. Yeah, I think that's right. Fine. Fine. In fact, that's
In the third definition, both blocks are similar.
what? What?
The third definition,
Uh-huh.
LHS and RHS blocks are similar.
They look similar, but they're not the same, because you should think of this as having a Z1, Z2, Z3, Z4. And in this one, the ones that are fused are not Z1 with Z2, but Z1 with Z3. Okay? So the group theory analog of this would be the following. Suppose I have two fundamentals and two anti-fundamentals. So I have, let's say I have fundamental with I and fundamental with J. Okay? And then an anti-fundamental with M and an anti-fundamental with N. Now you can make a singlet by fusing this and this and this and this. So that's delta I M, delta J N. But you could also make a fundamental by fusing this and this and this and this. Okay, so that's delta I N, delta J M. Okay, clearly these are not the same thing. The space of singlets is two-dimensional. Okay, so it's similar but not the same. It's similar once you, it's the same once you do some mapping of indices. And in the case of conformal blocks, also locations. Yeah, okay. And your point about these being basically the same thing is really what we're going to try to prove now in some careful way. Yeah. Okay, let's see. Just give me 1 minute. Your question, I feel I haven't answered it completely correctly. Okay. When you just good. Right, how could it be anything otherwise, right? How could it be anything otherwise? Okay. Let's see. I think what you're saying is right, but somehow I think I'm going to contradict it in a bit. But okay. 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 Yeah, and by a constant, and this is the most confusing. Anyway, let's go through this and then we see. Now, what we're going to try to do is to look for a relationship between A and B. Basically, A times B is identity, that kind of thing, that kind of relationship. Okay. Now, let's look at the following. I'm going to just imitate the derivation. I'm going to just present the derivation that is given in this big yellow book, and then we will examine it. Okay. What these guys do is the following. They start with I star, K, zero, J, and J. Okay, so let's see, what does this mean? Okay, yeah. So what does this mean? What we have now is a theory on a torus. Okay? And this circle that we're looking at depicts the time direction of the torus. Okay. Okay. So This conformal block depicts insertion of an operator k, operator j, and operator I, three insertions at different times on the torus, at different times in the time circle on the torus. Okay? Now, what does this mean here? If we've got the time circle of the torus, at any given point in time, we can slice the torus, and we have whatever's running in that torus belongs to the Hilbert space of the theory. The Hilbert space of the theory can be decomposed into the Hilbert space, which is given by the Hilbert space of the primaries and all their descendants. Okay? So, what we mean by a J in the middle is between the insertion of k here and the insertion of this J, the state that runs, we demand is the states in the primary and descendant level J. Okay? There we demand that it's 0 running and so on. Because we're looking at everything that includes primary and all descendants, we can do this projection is conformally invariant. So this is the torus analog of a conformal block. If the full 3-point function on the torus can be written as some linear combination of all these conformal blocks. Okay, we're going to be studying this object.
So this O I star J are running with time, they are time dependent.
Didn't understand. Say, ask your question.
This middle O I star and J, are they time dependent? They are running with time.
They are states running over some part of Euclidean time. So it's just like in that part, it's just Euclidean time evolution. Yeah, so they will evolve according to their energy.
But IJK will not. IJK are fixed in
At fixed times.
but these are evolving.
Yeah, so those external lines are operator insertions, and in between represents evolution of states. States in Euclidean time. Okay, is this clear? Now, this has not been very accurate so far. This was okay because it involved a fusion of j with j to give you 0. This was okay because it involved a fusion of 0 with I to give you I star. Yeah, I with I if you did it in the right way. But this guy has 3 different things. So I need to say with what, what particular fusion. So it's also labeled by beta, by some beta. Okay, is this clear? Fine. Now what I'm going to do is something totally weird. Weirdness has to do with these numbers. And just 1 minute more, let's go back up here. Okay. Hopefully by the end of this lecture, all of us, certainly including myself, will understand this derivation better. Okay, let's see. Okay, fine. So let's take this guy on the left hand side again. Okay. Now I'm going to do a sequence of operations on it. Okay, I'm going to take the same object and write it equivalently in some other ways. Okay. So the thing I'm going to do first is the following. I will fuse, yeah. So the way I'm going to think about this is here. I take this guy, this is connected, and I make some of the connection dotted. Okay, so you think of this as 0, 0, and these two zeros are later going to be fused. Okay, so now once we've broken this connection, we will have to rejoin it later. But once we've broken this connection, we can take this guy, which is 0j, j ki, okay, and do crossing on it. Okay, this is a very trivial crossing, because you see, when 0 fuses with j, it gives you j trivially. This is just nothing. So this was really representing a 3-point function, okay, between j, k, and I in the beta fashion. Okay? I star. I star depends on which way you look at it. Okay, fine. Yeah. Okay, but I'm going to just write that as an example of crossing, just so that you get used to this. Okay, so what I do is I take this thing. So let's look at it down here. Let's look at it here so that we can not muck up our final diagram. So we had 0, j, k, and I star with beta. Okay, and that's now going to be the same as 0, I star. Okay, then whatever you get, but when you fuse 0 with I star, you can only get I star. Okay, I star, j, and k in the beta fashion. And this is totally trivial equation, because both of these represent the same 3-point function. Okay, it looks like a 4-point function, but since the 4-point function, one of the 4-point guys is 0, you're doing nothing. Okay, but these manipulations we will do for the next 20 minutes, so let's do it in this way. Okay, so what I do is now I make that replacement. Yeah, I just fuse now, instead of fusing 0 with j, I fuse 0 with I star. Okay, and this coefficient this is not, so this is equal to this, because both of them are just 3-point functions. We've just written them differently. Okay, so now we will write that in the following way. We fused 0 with I star, and so now we have this 0 is fused with I star. This is equal to 0 is fused with I star, and then I star runs in I star, and then we get k and j with a beta. That's this part of the diagram we've just redrawn. Okay, but the remaining part of the diagram had this I going to an I, going to this 0 joining with the 0 that met this I, which was this I. Right, I've just rejoined this dotted part. This I star was joining an I, and the 0 was actually also joining that I. Okay, so this diagram is the same as this diagram. Really, this is total triviality. Is this clear? Questions, comments? As I've mentioned, my understanding of this is, so questions and comments are very welcome. Okay, these kind of manipulations.
That second diagram, how the two are equal?
How the two are equal? How the two are equal? Well, you see, let's see what this diagram does. This diagram fuses j with 0, but that's just j, with 1, coefficient 1, right? Because identity is nothing. Okay, and then j goes and meets k and I star. So this is representing a 3-point function of j, k, and I star. Look at this diagram. This is also representing a 3-point function, j, k, and I star. So it's the same thing. It's just fancily written in some different way. Okay, you should think of this, but I wanted you to think of this as a particular case of crossing, when we know, okay, in which case we know the coefficients. We know the coefficient for this Gaussian channel is 1. The coefficient for everything else is 0. This is just equal. I mean, because they're both just the same 3-point function. So this is equal to this. Now I do something a little more interesting. I notice that once again I take this and I break it here. So this was I star, this was I star, or what, I don't know, that's convention. I suppose our conventions would be that this is I and this is, and if I goes in here, I star comes out here. Oh, sorry, this was 0, sorry. What am I doing? This was 0, so yeah, this was, right, I star I. Great. All clear? Now I've broken this, I have to rejoin it eventually. But once I've broken it, you see that this part is an I star, I, 0, I star. This part, I've just drawn this part, and then this I star itself is attached to other things. And this is the dotted line. Is this clear? Yes. First I broke this. Then I'm removing all this stuff. That's what's attached here. In your mind, just remove this stuff. Once this is broken, this has what external lines? I star, propagator 0, and another I star. That's what I've drawn here. I star, that's these two. Propagator 0, I star. And then these I stars have to be attached to this stuff. Beta with this is still there. I'll draw it. Beta with a K and a J. Okay? But now that I've drawn it this way, you see what I'm doing. This I star 0, I star could be replaced by mu I times the other way of connecting. Okay? So this is equal to, okay, now we have to be a bit careful. This replacement is a projection. Okay, so what this is really equal to is every way of running of I star I M I star, and then this guy, and then this guy goes to J and K with beta, and then you sum over all M with the right coefficients. Okay. However, and the dotted guy is joined now, right? These guys are joined. Okay. However, we are interested only in keeping this 0. Now, why are we interested in keeping this 0? I star I. Not clear. In group theory, J and J can fuse to give you 0, but can fuse to give you other things. Right? So that's not clear. I think, give me one. The part. Okay. This is always, of course, true once we include everything. But You see, yeah, give me a minute. Maybe when we go up in energy like this. Yeah. For some reason they're keeping only the 0 here. Give me 1 second. I suppose we're keeping the part. I suppose we're keeping the part. There's the whole thing, and we're only keeping the part. Okay. If we've got this whole thing, the part of it that has 0 running here is equal to mu I star I 0 I star j k. Now, first, at least, is this part correct? J k I star I. That part is what they have, mu I, and then I suppose there's plus dot dot dot. I don't see any reason for that not. Okay. As far as I understand the manipulation, the conclusion of this manipulation is that this object has this piece, and plus dot dot dot, where dot 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 is of the form I star I m zeta I star j and k. Is there in? I see no reason for this to vanish. And so these things should also be there. If you read this book, I should actually read the paper. I haven't yet done that. I should read the paper where this is done. But you know, what is equal, what is approximate, what is up to projector is not very clear. But okay. But anyway, fine. We'll follow our logic and see where it goes. Great. So this is point number 1. Now, that was manipulation number 1. Now we want to move on to manipulation number 2. See, manipulation number 2 is very similar to, you'll see. Okay. Let's move on to manipulation number 2. There's I star, there's k and beta. Okay, there's j, we have 0, and we have j. That's the thing we're starting with. Now, what we're going to do is do the following. Yeah. So, what we will do is break this guy. So, for instance, what we'll do is here make this dotted. So this was a beta, this was a j, this was also a j. Is that what we want to adjust? Yeah. Right. The reason we're doing that is now this is an II star, a 0 and a JJ star. And that was the thing that was designed for the use of this A matrix. Okay. So what we have here is this I star, 0, J star. Okay. And this, if you remember, was the same thing as A alpha beta I j k, and now I j k alpha beta I star j star. Right? So we just plug that in. So we just plug that expansion into here. So now what do we have? We've got ij, well, of course we have this A alpha beta, ij k, we have a sum over everything, and now we've got k I star j star, and now the j star would be attached to the j, that thing which, and this is attached also to this, which becomes a k with a beta. So now we should be a bit more careful. We'll call this alpha and zeta.
There are two Ks. One K is full summed over and
We'll call this m. Okay. Excellent. Right, that's also what they have. Okay. And then we will do what you wanted. We'll try to undo this. Okay. So, but undo it in an opposite way. So just give me a minute. So what we're going to do, yeah, okay. So what we will do is now cut this I. So not quite undo it. We will cut this I. So here this was dot dot dot, there was I star, whatever, I star here. Okay. And now we will look at this scattering. This guy being exchanged, this guy being exchanged, this J star being exchanged. Okay. So we have I star with K, and is that what we do? Just 1 minute. B has, we want I. Just 1 minute. That is not changing. Yeah. These were both, oh. We got these with both M, with both K's. Now where did that come from? we had this M here. What they did was to look at the part of this that is M equals K. M equals K. Okay, I'm really sorry about this, but this is the correct thing, and so this is equal to A alpha zeta I j k zeta I star j star k plus sum over m not equal to k, the same stuff, right? This, yeah, okay. K beta. And for some reason they're keeping only this part. This is some other project, some P prime. Discarding this. I suppose the point will be that that will be the same as the discard of this. We'll come back to that. I'm sorry, I only half understand it. Okay. Let's go on and see if we can make sense of it. So we keep this part. Now when we've kept this part, now we can cut this. We'll have to rejoin. Now we have an IK, IK, KI kind of scattering. Okay, so now we can use B on that. Okay, so we can use B on that. And when we use B on that, that becomes
You operate that as running in the lower end with J star.
J star. That's the tree level exchange. It doesn't matter what runs, right? As long as, let's remind ourselves what B was. I'll write it down, it's too slow. Let me remind you, as long as we had I, K, alpha, J, beta, I star, K star. That had various things, but we had this B alpha beta times I star 0 K K star. Right, so here in the same way we have I star scattering with K, in this case, let's point to where it actually is happening. So we have this I and I star, where were we? This M is K, right? So we have I and I star and K scattering with I and K with the exchange of J, just like him. Break this.
So
I and this M, which is a K. Okay, and here once again there's a K and an I star. So equal and opposite in pairs like this. Scattering with tree level exchange of some J. That is this tree level exchange. So that's built for this use of this B.
But in the equality that you wrote, you also have to use some projector, right?
Yes.
It will again be something
Plus other stuff. Plus other stuff. Yeah. Right. Okay. But let's just go through it and see what we see. Okay. So this stuff is basically telling us you put your I and your I star together. Together you get this. You get 0 with this B. Okay. I'm not being so precise. You get 0, and then you get K star this k, that k goes to ij, and this k is just what it is. As you said, this 0 could have had other things running, and it's a very similar kind of projector from here. Once again, it's this kind of bubble with I and I star and a 0 running. But there was an earlier projector as well. Okay, so fine. Okay, so second projector. And then they do a third. No, I think that's. Yeah, that's it. Okay, that's it. Now, what you've got is this. What we've got is this I star I with 0 here. Now, okay, let's compare the two final diagrams we had. The two final diagrams we had were, there was this, which was I, 0. I'm only keeping the path that they want for whatever reason. I star, but I star. It's going around in a loop. Then I star, and then k and a j. That was what we had on the left hand side. On the right hand side, we have I. Now we have a j. K, 0, I star, and k. Okay. And these are almost the same, except you see, when you do here, you have this j, k coming, and then there's a j. What is running here? These two they claim are the same. This must be some obvious thing. Just
I mean, you could just shift, can't you just shift this loop, this bubble, this tag?
yeah, you can, because it's 0.
Yeah.
Because it's in the identity representation, right? Because of that, you can just move it around. Yeah, so that's exactly it. Because it's in the identity representation, doesn't depend on where it's located. Okay, so you can move it around. Yeah, so I think that's basically what's going on. That's basically what's going on. And so they claim that this thing. So what is the end result of all of this? The end result of all of this is, now if you keep track of, I haven't done this so carefully, but if you keep track of all the indices carefully, on the first manipulation gave us a mu I times this object, and the second manipulation gave it to us with an a b first with a b, and then with first an a and then a b. Yeah, so A and B, but you act first and then this. Yeah. Okay. And now you have to keep track. These B's had these ijk's, which are constant in the whole thing. But what was important was this alpha and beta. And the claim is that when you follow this carefully, I haven't, because I understand it so poorly, I didn't follow it with all indices. But the claim is that when you do this, you'll be summing over beta but keeping alpha fixed. Okay, and this is a key equation that they claim is true. Now I know I've far from derived it for you. And we will come back to this. I will actually, there's a paper by Wallende and Dijkgraaf, which this is supposed to summarize. I will read that paper and come back to you. I'm sure the final answer is right. Maybe, I can't remember. Yeah. It's the paper that follows Verlinde's. Verlinde originally wrote this paper on the Verlinde formula, in which he presented it as a conjecture. Okay? He presented it as a conjecture and checked this conjecture against many examples and was correct. And then they wrote this paper claiming to derive it. Seiberg and Moore have also claimed to derive Verlinde formula, and various contexts other people have claimed to derive it. I believe that this derivation follows the analysis of Verlinde, and Dijkgraaf. And I'm sure their paper will be more understandable. I'm so sorry that this this yellow book is normally a good source. I should have prepared more than an hour before this lecture, I'm sorry. Okay, fine. But let me continue. You see, we come back to this next lecture on Friday. I will clean this up. Okay. Let me continue from, so what? We've got these A symbols, we've got these B symbols, we've got the mu symbols, we've got a relationship between them, so what? Okay. Now, I'll tell you the so what at least. And we will come back to the derivation and clean up its bits as we go along. Now, the reason that this A and B are of relevance to this question of crossing and N is the following. Look, what we want to do is to take what we want to do is to deal with these characters on the torus. So, a character on the torus is like, let's say, some state j running on this thing. This would be what we call chi j. Okay? Now, chi j is also equal to identity inserted when j is running on the torus. I've done nothing. Okay, so this is with the j. Now, I can also make this as follows. It's because I and I star fuse to identity. This is equal provided, this I is at location z, this I star is at location z bar. When I and I star come together, they fuse to identity with the 1 over z minus z star, z1 minus z2 to the power 2hi. So, if I take this object and I multiply it by z1 minus z2, z1, z2 to the power 2hi, and I take the limit that z1 goes to z2, that is the same as this. Okay? So, this character here is the same as this quantity. Okay? Always understood, limit z1 going to z2. Okay, so far we've done nothing. Now, Verlinde and friends ask the following question. They ask, great, when these two guys come together with z1 equals z2, that's what this is. But what happens if I take z1 and z2, or let's say I keep z2 fixed and take z1 around the time circle, so that it comes back to z2 and once again fuse to 0. Okay? What happens when I do this? If I take z1 around the space circle and once again fuse to 0. This is the question they asked. Okay? This is sort of the key physical element in this derivation. Okay, so first let's deal with the space circle. Let's suppose we've got some two operators here and they start off very near to each other. Then I take one of them and I take it all the way around the spatial circle. So I take it around here and comes back and fuses. Now, this operator, once it's fused again, it has no insertion point left. And because these two have come and fused again, so this property is the same conformal properties as a character with no insertion. Okay? But if you cut this character here, the state that was running was j. That was not changed because you put these insertions at some given time. Right? This is a trace. It's j coming this way, and some trace. Yeah. And now this insertion point has gone away, at least as far as conformal properties is concerned. So clearly this is going to be proportional once again to chi j itself. Okay. So this operation of taking this operator around in space on chi j, that is the operation they call phi a. A being a cycle on chi j was equal to some gamma j times chi j. We will discover what gamma j is eventually. Okay. Had we done this operation by taking, the 2 points around each other, for instance, and then refusing them, that gamma j would have been e to the power 2 pi I times hj, because you would have picked up the phase of one guy going around the other. It's that kind of thing, that kind of object, except now it's on a torus. It comes from the fact that these characters are multi-valued objects. They're not functions. Okay, excellent. This was the easy part. Then these guys asked, what do you get when you take these guys and take them across the torus along the B cycle? The question is, what is phi b on chi j? Okay, I'm now going to explain to you what you get. Okay, what we had was this guy. What we had was I star, and with the j going around here. Now, you see, this guy was going in the 0 channel here. By the way, physically, let's understand this first. What we've done now is take I and j and separate it like this. Okay? And then the separation goes all the way around the torus. So what you have is the state j coming like this. Then it meets I. Sounds reasonable that the state you're going to get is whatever, it's clear. The state you're going to get is whatever is the fusion of I and j. So what you will have is, over the region where we separated I and I star, the states that propagate will be neither j nor I, but all the states that appear in the fusion of I and j. And then you take it round again, all that remains is all the states that were in the fusion of I and j. So it sounds reasonable that what you're going to get is a linear combination of characters for all states that appear in the fusion of I and j. The question is, with what numbers? Okay? And that is the question these guys address. Okay. So what we want to do is to take this I and j around the time circle. Okay. So in taking it round the time circle, once we've taken it around the time circle like this, it's inappropriate to fuse I and j like this, because they now have separated very far, because you've gone around the time circle. So what we want to do is to undo this fusing and then redo it on the other side of the time circle. So take this guy here to there and fuse it like this. Those are the set of operations we're going to do. So we're going to break up this fusion. Okay? Now this is sort of easy, because you see this was equal to I star 0 j star and then dot 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 dot. Okay, but this was built for this A operation. This is equal to A alpha beta. I'm not writing the I j k. Okay. I j k, that's alpha beta I star j star and then this dotted stuff here. Okay? This, by the way, if you think of our physical picture, is the state that's running in the middle. K is the state that's running in the middle, because it's what's running between I and I star. Okay? Now, we want to take it round to the other end. We want to take these other insertions to nothing. So we want these I and I star to be basically, whatever, this K, we want it to run in a loop. I think that will give you the character of that thing. You've taken it all the way around. Is this clear? Okay? So, now, we rejoin this. This was this. And then we cut this. So we make this dotted. Okay? So this was K and I scattering by exchanging J to give once again a K and a K star and I star. Okay? So we do that, and provided we are allowed to use only the projector, this is the B operation. Right? Because this is a Kj through an alpha, Ki with an alpha scattering with tree level exchange of J, with I star K with a beta. This gives us like a B operation, provided we'll see that assumption in a minute. Then there's some B, whatever. So let's see what the joining up is. So what this does is rejoin it like this. So that was, it's K, K star, but those were connected, so that now they close up. We're keeping only 0, there may be others, but we're keeping only 0. Then there is the I star, and the J has gone. Right? So there is this I star J, and now we can now take these guys around, fuse them again. Okay? And this stuff here, okay, is just the character then of K, chi K. Okay. So, schematically what we have shown is this. Phi B on chi J, okay, phi B on chi J is equal to A alpha beta, B alpha beta, okay, phi chi K, where this alpha and beta is associated with I, J, and K. Okay, and this is summed over alpha, beta, and K. Okay. Then there is one more element. The last element is the following. The last element is this. The last element is this. Now this, you remember that we claimed we had derived A alpha beta, B alpha beta, sum over beta but not alpha, sum over beta and K but not alpha, is equal to mu I. Okay? This has an extra summation over alpha. Okay? That extra summation over alpha runs over how many variables? N, I, J, K. Okay? So that summation over this gives us N, I, J, K times mu I times chi K. And there is an argument which I haven't yet understood, which I will try my best next class give you is that this, saying that this was phi b is naive. Actually, this is mu I times phi b. What the sum of operations was actually mu I times phi. Why I didn't get it, but okay. So the claim is that these mu i's cancel, and what we have concluded is that phi b on mu j, chi j, is equal to nij k chi k. This is the key equation that we're going to use. Okay, I very much acknowledge that the quote-unquote derivation has about 20 flaws in it. I mean, these are flaws in my own understanding. I'm not saying there are flaws in the derivation. Sure, the derivation is correct. Okay, I just don't understand it yet. But this is the final answer that we were go after. Okay, I will try my best in the next lecture to do a little more study of the original literature and make up the flaws of this derivation. I hope I will succeed. Huh? No, B is the time circle. A is the space circle. A had trivial. It's separating in the time circle that gave you this non-triviality. Okay, the key point was that this separation here, that it is a linear sum of chi k's is obvious. Only those k's that appear in the fusion back. What is interesting is that it appears with these exactly with these coefficients. Okay, so that this phi b acting on chi j is n ij ijk phi k with exactly those numbers. This is the claim. Certainly it is a claim that is easy to verify in minimal models because you can just compute the fusion coefficients, you can compute. Okay, you can also, I have myself derived these things in Wess-Zumino-Witten theories just using a path integral derivation of these things. Okay, so it's certainly correct. The answer is certainly correct. The derivation is doubtless also correct. I will try my best to understand it. Okay, so this is the final thing. For the next 10 minutes of this class, what I will do is use that equation. I don't understand exactly how it came. I've sketched the elements as presented in the yellow book. If one of you have the energy to read this part of the yellow book and discuss with me or come and discuss next class, if you understand it better than I do, great. I will try to look at the original papers. Can't understand what the hell they're saying, basically. But let us take this equation and then proceed. Now the consequences of this equation are very clear. They're very clear because we know two things. We know that phi a on chi j is equal to gamma j on chi j. This we know. And we know that phi b on chi j is equal to n I j k on phi k. Somehow we believe this derivation. But we also know that A and B are interchanged by modular transform, by tau goes to minus 1 by tau. But under tau goes to minus 1 by tau, the characters are acted on by the S matrix. Okay, so if we do this modular transformation, okay, we conclude then that this Nijk, okay, S with S dagger or S inverse, but it's a unitary matrix, okay, is this gamma j. So we conclude that these n, when I've written this S and S dagger, I'm using the matrix notation we developed when, for instance, we argued that the n matrices commute with each other. Okay, so this is the Nj matrix whose elements are I, K, and then you act with S and S dagger. Okay, that is that object is is just this constant gamma j times identity. Okay? And therefore, we see that this n matrix, all the n matrices, are simultaneously diagonalizable. Okay? They're simultaneously diagonalizable, and the diagonalization, the eigenvalues of this, the matrices that diagonalize them are the S matrix. Okay? Just because the S matrix interchanges A and B cycle, A cycle acts trivially on this basis. Okay. Okay. And when we pursue this a little further, you can use this to find a very explicit formula for. So you can write n as equal to S gamma S dagger. Okay. So this is this diagonal matrix whose entries are gamma 1, gamma n. And then using the fact that, anyway, we'll do all this next class. Using the fact that n 0 ij is just delta ij. Because if you fuse 0 with I, the only thing you get is j. You can read off, and then you can read off formulae for what this gamma is in terms of S and so on. We'll do all that next class. The important point is that once you have this formula here, immediately you see that there is a connection between this n matrix and the S matrix. And the connection is that the n matrix is all the n matrices are simultaneously diagonalized by the S matrix. And with that you can very quickly give an expression for n as a in fact there's a function I'll explain this next class. So there's a formula for n in terms of these s's, just 3-4 more line manipulations from here. Okay, won't pursue this because it's not very satisfying till we understand the derivation. So I was thinking of, I think we'll stop this class here, apart from discussion, questions, comments, any that you have.
Yeah, sir, so I want to understand this, we are going to get to A and B.
Yes.
How it happens
In the same way. Okay, good. Excellent. Consider a torus like this. We have a character which is a trace and a definite representation along this cycle. Now, you consider 2 points. We were interested in them fused, but now we're going to separate them. First, separate them along the spatial cycle like this.
in a fixed time.
At a fixed time. And then bring them back along. Bring them back and fuse them again. Okay? Now, you see, let's look at what the states running at any other time other than the time you put this thing. That is clearly the state in chi j. Okay? So this is this object that we have is some object that has receives contributions only from chi j's. Okay? Now it receives contributions only from chi j's, and because you've refused these points, it doesn't depend on the location of a point. So it's conformally invariant. So the only thing that has this property is that it's a trace over things that receives contribution only from chi j's and has no other insertions. Of course, if you had other points in the game, there could be correlation functions. Because you've refused this, it doesn't depend on that. The only thing that has this property is chi j itself. Okay? So this one is a very trivial one because it's happening at constant time. It's not changing what's happening to the states like this. Now let's look at the other guy, which is less.
This state is same as chi j.
That any earlier time or later time, clearly it is.
It was chi j, so the separation will also.
Once you fuse this again, it's just some constant times chi j. Right? That is the very trivial one. What was much less trivial was this. Suppose you take this, put it here, and put this here. Up to here, what state is running? It was j. Now you've got this operator insertion I. Now let's use state operator map.
So these are Z1, Z2, right?
These are 1 and 2, yes, Z1, Z2. What we're getting is a state that we get by acting on a state in the module J by an operator in the module I. Okay? If we did this here in radial quantization, we had a state in the module J that we could make by putting an OJ. Then we act with an operator in the module I. But you know that now if you do the state around here, you get everything in the fusion of I and J. So it seems intuitively clear that what you're going to get here is in this region we will get states in those Hilbert spaces that lie in the fusion of I and J. Okay? So everything that lies in the fusion of I and J we should get here. And then we're going to take it round once again and fuse. So the way I've written it here, this was part of the answer. Then there were some matrix elements and it was tied up with some propagation of state J. But we've removed that part of the state J. So it seems, again, intuitively clear, for the same, using the same reasoning as before, that what you'll get is a sum of characters, only those characters that lie in the fusion of I with J. What is incredible is that the linear combinations, linear coefficients of this are precisely the fusion coefficients. That it's these characters is clear, I think. What is incredible is that what it appears with integers, Nijk, that is far from clear, at least to me. Okay. This part was what that earlier derivation, that no derivation. I was just explaining the words said in this yellow book, and if you found what I said incoherent, wait till you read the yellow book. Wait till you read the yellow book. Okay. Okay. Please do, by the way. Okay. But I'll read this paper. Hopefully, I'm hoping that either by reading the paper or by talking to Abhijit, who maybe understands this, I will give you a proper derivation next class. And then I will pursue the consequences more systematically. Okay. I'm sorry for the quality of this lecture. Okay. Yeah. Yes.
You are treating N as a matrix plus indices
Louder, please.
you are treating this Nijk
Yes.
as a matrix
Yes.
with indices with left and right indices J and K, right?
With left and right indices J and K. Or maybe I was I think I was treating it as N, this index. I wanted this to be a diagonal matrix whose values were, you see, this object, let's look at this object. This phi A acting on this thing is a diagonal matrix whose eigenvalues are gamma J. Okay. So I want to end up with a diagonal matrix whose eigenvalues are gamma 1 to gamma whatever. Okay. So I want the matrix indices. No, so I'm treating it as Nj is the matrix, Ni is the matrix, I is the matrix, and Jk are the elements. And this will be a diagonal matrix whose elements are gamma J.
You're multiplying, I mean, when you take this, when you write N in this bracket,
Yes.
you're summing over J.
I'm summing over. It depends on which one is the matrix. Let's derive that more clearly. Let's do that. That part I think we should. Okay. So let's see. So suppose we have that phi b on chi j, okay, is equal to n I j k chi k. This phi b, of course, is phi b I. You take I across. Okay, excellent. Now, let's take these chi j's and represent them in terms of chi j of -1 by tau. Let's do the modular transform. Okay, so phi b on sjm chi m of minus 1 by tau, okay, is equal to nij k sk q chi q of minus 1 by tau. Okay. Now phi b acts on this guy diagonally. Okay. So phi b, this guy just gives us a gamma m. Okay. So the action of this on phi b is a gamma m. And now we can, let's write it the other way. So let's take this s here. Okay. So we see that, so let's take this s here. So now let's write this in matrix language. This was okay, let's write it with indices first. Sjm gamma m on chi m is equal to nij k sk q on chi q. Okay, so these two, this is true for, so now we make this m. Okay, and this is a basis, so we remove these. So this is our equation. And now we can multiply by Sm k prime inverse. So S inverse M k prime. S inverse M k prime. This gives delta k k prime. So this is with a k prime. Okay. So okay. Now, okay. So this is the equation in indices. So k prime here. And now let's write it in matrices. This is matrix multiplication Sjm. Then this is a diagonal matrix with only m. You know, so this diagonal matrix, and then this is S inverse M k prime. So this is written as S d S inverse. And its matrix indices finally are j k prime, right? J k prime. So this is equal to, so ni. Is this clear? Okay. So equivalently, B is equal to S inverse N I S. Where is I? You see, this D here has I in it because it's the operation of this gamma I. We made identity by fusing I with I star, and then we took it around. So it gives you a phase, this gamma j, which depends on which character you're acting on, but also on what operator you took around. Okay, so that gamma j, when I wrote it as gamma j, I should have been gamma j comma I. Okay, right. So that's that. Okay, good. Other questions, comments? Okay, since you're listening so carefully, let me say one more thing. Since maybe then this part let me just complete the. Now that we've got these equations on the board, okay, let's take this equation. Let's take this equation, the equation that has that we have for n, and let's set, for instance, let's set, for instance, let's set, for instance, j equals 0. Yes. So this is so we get the equation delta I k prime is equal to S 0m gamma m S inverse m k prime. Okay. And so right. So now we multiply by the inverse here. So we get, so this as a matrix equation. Let's do it. So we get S m, let's say, so I multiply by S k prime, let's say alpha, and then I get delta alpha m, right? So I get multiply by delta I k prime S k prime alpha. This is equal to S0 m gamma m delta alpha m. Okay, and so this is Si alpha but we can just make it. Okay, Si alpha is equal to S0 alpha gamma alpha. Right? And therefore, just dividing by S0 alpha, you can prove S0 alpha can never be 0. Si alpha divided by S0 alpha is equal to gamma alpha. So we found a formula for this gamma alpha, okay, in terms of the S matrix. Note it depends on I. It's gamma alpha because of this fusion. Okay? And now that we have this, we have a completely explicit formula for n. Because we had, n was S gamma S inverse, but now we know what gamma is in terms of S. Okay, so we get a formula which is SSS by S0I. Okay, so this is the final form of the Wallende formula, a very explicit formula for the fusion coefficients in terms of the S matrix coefficients. It's quite a remarkable structure because it relates to things that seem to have no connection with each other. The derivation should provide us intuition for this connection once I understand it. Okay, let's stop.